Thank you very much for the kind introduction, and to all of the folks here today, as well as the organizers for putting together this really nice session, this program, Trifon and others, for Naz, Paul here. Today I'd like to talk to you a little bit about conditional simulation, the problem of sampling conditional distributions. And before I get started, I want to acknowledge my collaborators, Aram Puladian, who really wanted to be here today. But I'm hopefully going to do a decent job in representing our joint work that in collaboration with Michael Brennan, Yusuf Marzouk from MIT, and John Niles Reed from NYU. So to introduce the problem of conditional sampling, I want to start off with two motivating applications. The first is one that maybe many of you have seen recently in the media. It's from the information sciences, the problem of the desire of wanting to generate new images given text prompts. So what a lot of recent models have successfully been able to do is to build a pipeline that can take a sentence like a cat and a frog or a large aircraft taking off and generate pictures that resemble that text prompt. And hopefully what we'd like these models to do is to generate many images that are representative of that text prompt that can really sample the diversity of images consistent with the prompt, and maybe give us an image of what a typical skateboarder looks like outside. The second example is one that I've spent a lot of time thinking about, which is that of inverse problems. It's a more kind of classical application of trying to estimate an unknown state or parameter that we'll denote by x, and this is a notation that we'll use throughout the talk today, given a noisy and indirect observation that we'll denote by y. These in inverse problems, what we typically assume is that x, the state, is related to the observation through some forward model, g, that takes in as an input x and maybe some observational noise or process noise that we can denote by eta. And what we'd like to do is to then, given an observation, a realization of y, try to infer back x. The x in particular that might have generated an observation that we see. If we want to do this probabilistically, what we'd like to do is not just recover x, but actually characterize the distribution of these states or parameters x given the observation. And this is something that from Bayes' rule we know is related to some prior distribution on x times some likelihood model, some model that relates x, the state, to the observation, usually as a result of this forward model. And this is something trying to generate samples from this distribution and characterize the uncertainty of the state that's consistent with the observation is something that is very important in applications throughout the geosciences, things like numerical weather prediction, where we want to characterize the atmospheric state and make predictions about how likely it is to be sunny tomorrow here in LA, given some observations. Or in other contexts, like trying to infer the trajectory of populations, of the financial markets, etc. Now, in both of these settings, this is a problem either in sampling images given text or sampling parameters given observations. It's this problem of sampling some unknown condition on another random variable. And we might ask, why is this a hard problem? Well, in both of these applications, we typically have a setting where the distribution over the thing that we want to sample over, let's say the distribution over all natural images or the distribution over the states of the atmosphere, don't really have a density that's known in closed form. So we don't have an analytical form for this distribution on the thing that we want to sample from. The second is the likelihood function that arises from this forward model that relates images and text or states and observations through the forward model. Might also not be easy to actually evaluate because maybe we don't really understand all the measurement errors that enter into this mapping. The third is we're often trying to sample very high-dimensional objects, like these high-resolution images. And the fourth is we typically want to sample, let's say, images given a text prompt that we might not have seen before. So we're in settings where we might just collect a very limited number of samples from different conditionals, like an image and a caption. We might have a collection of these images and captions. But what we want to do is sample new images given captions that are entirely different. So maybe we only see cats and frogs separately, but now we want to sample a cat and a frog in an image. And so this, as a result, classical sampling methods, especially for solving inverse problems that are typically based on evaluating the density for the state given the observation, and use the fact that you can evaluate this density up to a normalizing constant. These are traditional Markov chain Monte Carlo algorithms are not really tractable in a lot of practical settings for both solving inverse problems and these data science applications. And instead, one problem that I focus on a lot is that of simulation-based inference. So here the problem is the only assumption that we make is that we can sample parameters from some prior distribution. So in the context of these image generation problems, we can sample a natural image. We have some process that can map that image to an observation, like a text caption. And together, these give us pairs of samples from the joint distribution of states and observations. And what we'd like to do is to sample an arbitrary conditional of this joint distribution, just given pairs of samples from the joint. So in the talk today, I want to discuss how we can look at this problem using transport. So I want to discuss this in 5 parts. So the first is going to be on how we can use transports for conditioning. The second is to propose a non-parametric estimator for these transport maps. The third is I'll present some analysis of the estimation error related to these maps, and lastly, present some numerical results. So first, in terms of transport maps. So this, non-surprisingly, is something that in this workshop we're all likely have seen several times. What we're interested in, or what I'm interested in to address this conditional sampling problem, is to look for map T that pushes forward some reference distribution, like a standard Gaussian, something that we can easily sample from, and can take it to ideally an arbitrary conditional that we're interested in. So a conditional of for the state given any a realization of the conditioning variable. Now, if we had samples from some reference, like a standard Gaussian, and the conditional we're interested to begin with, then we can just apply our typical estimators. The question is, how do we learn such maps when we don't have samples at all from the target conditional that we're interested in? And so the approach that we're going to use is that of trying to build a map that takes us from a reference to what we do have access to, which is the joint distribution of states and observations, such that we can use part of this map to also sample the conditionals. So what we showed in some recent work is that if we consider a map here T that pushes forward a tensor product reference measure, just think of it as a standard Gaussian rho. But any measure actually will do that factorizes into two marginals, rho of Z1 and rho of Z2. And we find a map T that pushes forward this joint distribution rho to mu, the joint distribution of x and y. But we don't look for an arbitrary transport. We look for a map that has a particular, what I call a block triangular structure. So it's a map that can be partitioned into two blocks, here denoted Ty and Tx, such that the first part only depends on the first variable Z1, and the second depends on Z1 and both of the inputs, Z1 and Z2. If we find a map T that pushes forward rho to the joint mu, then the first component of this map will transport the first marginal rho of Z1 to the first marginal of this joint density mu, so mu of y. And the second block, for every value of the first argument, Z1, is a transport map that will push forward the second marginal rho of Z2 to the conditional, the remaining part of the joint distribution of x given the observation, something related to the observation y. In particular, what we often take is, because we have the freedom of choosing the reference measure, we can take the first marginal rho of Z1 to be the marginal of the observations. And so then map Ty that transports mu y to mu y is, we can just take it to be the identity. And then all we're really looking for is the second component of this map that transports a standard Gaussian and is parametrized by y. So it transports a standard Gaussian to the conditional of x given each instance of y. And by simply plugging in any observation y, we can simply sample from any arbitrary conditional we're interested in. And just to kind of visually have a visual depiction of what we're dealing with here, what we might have is a joint distribution of two variables x and y that might transport, let's say, a Gaussian to this, my favorite two-dimensional distribution, this banana. And what we'd like to do is to generate samples from conditionals, from slices of this distribution. So these these horizontal slices here. These horizontal slices, we can see they're one-dimensional densities in this first column. And on the far right column, I plot actually the transport map that would take standard Gaussian to each of these distributions, going from this unimodal distribution at y equals to 0 all the way up to this bimodal distribution. And this map is really parametrized by the conditioning variable that we're interested in to sample from. OK, so the one recipe to do this kind of conditional simulation, and especially this is something that's known as amortized inference, because what we want to be able to do is to build these maps that allow us to amortize the cost of inference over any value of the conditioning variable, is to generate samples from this joint distribution of x and y, these pairs xi, yi, to learn this block triangular map. And then given a particular conditional we're interested in, y star, we can simply simulate then from the conditional by evaluating the map tx, the second component of the map, at y star and some standard Gaussian, some reference samples. And I would say that this is really the picture to have in mind that goes underneath a lot of recent conditional generative models. Things like conditional normalizing flows, conditional GANs, even conditional diffusions. Really, they're taking samples of a joint and then just learning this parametric dependence on the conditioning variable. Yes.
If I may ask, so the first block of T you assume is the identity map, right?
Correct.
So a new observation Y star may not be in that empirical distribution of Yi's you observe. So
Correct.
you need to kind of do something there, right, here?
Correct. So we're learning on the basis of some empirical. That's really the key aspect, that you're learning on the basis of only having a finite number of y's, but you really want to learn this map that can extrapolate out of distribution for the.
So you have to smooth that map in some sense.
Correct. Yes, thank you. And we'll get into that in exactly a second. Yes. So these can be typically implemented with these. Different generative models that actually do this kind of smoothing in a bit of an ad hoc, if I can say, way. Okay, so the typical approach to learn these maps is to use variational approaches. So one might introduce some type of divergence or metric between probability distributions, here that I'll denote by D. And the idea is to, given this joint distribution mu, to search for these maps that minimize the divergence between the target mu and the push forward through this Gaussian reference of the map T. So as an example, if we're working with the KL divergence, which is very common for one class of generative models known as normalizing flows, then solving this problem corresponds to solving a maximum likelihood estimation problem for the push forward density of the map through the Gaussian reference, which you can implement just given this collection of samples from the joint. We can empiricalize these objectives and then solve this maximum likelihood estimation problem to get our estimator that we can use to then sample from the conditionals we're interested in. However, so far, all that we've said is we have, if we have two, a reference and a target distribution, and we look for these block triangular maps, and the block triangular map satisfies the push forward condition we're interested in, then we can use it to sample conditionals, but we haven't really specified what is one particular map that we'd like to target. In fact, there's many block triangular maps, as we all know. One that is near and dear to my heart is the Noth-Rosenblatt rearrangement. That is one that many of you might already be familiar with. It's the strictly triangular map rather than just the block triangular map. So it's a map, let's say if you're mapping from RD to RD, where every component is just a function of an increasing number of scalar variables. But in fact, even just if we permute the ordering of the variables of this map, for every ordering, we get a different map. And all of them can be we can construct many versions of these block triangular maps under different orderings using these KR rearrangements. So far there's no, there's a question of which map should we choose when we want to build these block triangular maps. And so today I want to focus on one approach that actually has explicit guarantees for the number of samples required to estimate this map, and is different than many of the typical approaches up until now of these generative models that often require tuning a lot of hyperparameters. We really wanted to, in this work, try to come up with an approach that can be more that can be implemented more generically with general data sets. So what we're going to focus on is an estimator based on entropic optimal transport in particular. So and this really relies on two main results that we're going to rely on from Carlier and co-authors, which is the first is what's something that a term that we coined the conditional Brenier map. It's the idea that if we want to learn a transport from some reference measure rho, let's say of Z2, to a distribution of X conditioned on some additional variable Y, then we can, just like in the standard OT problem, we can find a map that satisfies this push-forward condition for all observation variables Y, which is the gradient of a convex function with respect to the variable that we want to transport. And moreover, it's a map that minimizes a transport cost with respect to this reference input variable Z2 in expectation over the conditioning variable Y. So Carlier showed that we can find such maps. But moreover, in some work that's actually related to these, trying to show a relation between these strictly triangular Noth-Rosenblatt maps and Brenier maps, what he and co-authors also showed is that we can identify this conditional Brenier map, this triangular map, as the limit of a sequence of standard optimal transport problems that don't impose any kind of triangular structure on the map. So what Carlier showed is that if we consider a cost function, here denoted by CT, that is the standard Euclidean cost for the two variables, Z1 and Z2, but on the second variable, we scale it by some parameter t greater than 0, some small parameter t, so that we're putting a much higher cost on ensuring that we transport the first variable correctly. And we look for the optimal map with respect to this scaled cost CT, I'll denote that by TT, that satisfies the push-forward condition of pushing forward rho to mu. Then as we take this parameter t to 0, then this map t that's optimal with respect to each one of these costs will converge to this conditional Brenier map, this block triangular map in an L2 sense with respect to the reference. So what we propose...
That's a quick question.
Yes.
So this convex potential C is jointly convex in Y and Z2 or just in Y?
No, it's just in Z.
Just in Z, sorry.
Yes, correct. Yeah.
Okay.
Yeah. So what we propose to do is, given that you can find these maps as a limit of a sequence of OT problems, we're going to construct an estimator for this block triangular map by just choosing a small parameter t, because going all the way to 0 in this parameter t could introduce, you'll see that the cost actually no longer depends on some of the variables. So we want to preserve some of always the dependence. So we're just going to choose a small parameter t greater than 0. Moreover, what we can rely on is the fact that because this is really just a reweighting of the standard Euclidean cost, then each of these maps for TT that are optimal with respect to this rescaled cost can actually be written just as in terms of a map which is optimal with respect to the standard quadratic cost. So if we have a cost CT, which is given by this quadratic form with any arbitrary weighting matrix AT in the norm, in this particular case, the AT corresponds to a diagonal matrix that has 1s for the first block of variables, and then the square root of t, this parameter for the second block of variables. Then the optimal map TT with respect to this cost can be written by computing a map T0, which is the optimal with respect to the standard cost from the push forward of the reference and the target measure by this matrix AT, And then just simply taking this standard Brenier map for the standard quadratic cost and composing it on either side with this matrix AT and AT inverse. So what this gives us is actually just a recipe in general for defining estimators for these conditional Brenier maps. If we're given data from two measures, rho and mu, we can simply rescale the data by this matrix AT, learn some estimator t hat 0 for the Brenier map between these two data sets, and just plug it in to get an estimator for this map, which is approaching a block triangular map as in the limit of t going to 0. So we can use any estimator for this map, for the standard Brenier map t hat. We can use, for instance, some entropic map. We can that my collaborators Aram and John really have worked a lot on. One can use nearest neighbor estimators for this map, like Tudor has worked on, as well as other more machine learning approaches that just try to estimate, let's say, those convex potential functions, and then just define the map through this learned potential. For today, we're going to just consider really this entropic estimator. So I don't think entropic OT needs a lot of introduction for the group here today. But just to kind of set some notation, so for the entropic problem of minimizing this rescaled quadratic cost plus this KL term between the coupling, transport coupling, and the product measure of the source and the target, one can write down explicitly the form of the solution for the optimal plan, and then define the entropic Brenier map, which is given by the conditional expectation of this plan, given a new input z. And what we can then do is construct a sample-based estimator for this entropic plan. Here we denote it as t hat that depends on two parameters, the entropic regularization parameter epsilon, as well as this parameter t that defines the scaling of the cost. This estimator, I want to highlight two aspects about it. You'll see that it's a linear combination of the target samples that I denote as z prime. But it's a map that depends on, that is a function of any z. So it's a map learned on the basis of a finite number of samples from the source and the target, but actually extends to any new input. So for instance, for the question earlier about trying to evaluate this map at a new value of the conditioning variable, such a map can be used, extends to that setting. Fortunately, as a result of a lot of recent packages, we can quickly estimate the potentials that are needed to define this map with a significant number of sample points. So I just want to briefly outline a few results on this estimator. It's not a complete analysis, but just what we can say so far. So the first analysis that we did is what was relating to the bias of this entropic map. So as we know, when you introduce this entropic regularization, we introduce a bias with respect to the true transport between that if we didn't account for this, we didn't introduce this regularization. And so we had a question of how to choose this epsilon regularization, this parameter, given that we also need to choose this cost, the parameter that defines this cost function. And we want to choose these ideally together so that we can define some consistent estimator for this map with respect to the rescaled cost. So for the analysis, both pieces of the analysis I'll mention, we considered Gaussian to Gaussian transport problems for the source and the target. Where in particular, these, of course, is a setting where we can compute the entropic map and the conditional Brenier map explicitly and do some asymptotic expansions to show that the error, if you choose the regularization parameter to scale epsilon as t squared, then it will balance the error coming from the entropic regularization and the error of introducing this finite t parameter, and the error will go down as t squared as t goes to 0. And so that gave us a schedule for how to choose epsilon in practice. The second is we did some preliminary analysis of the finite sample risk of this estimator. Again, we considered this Gaussian to Gaussian transport problem where we can explicitly compute the map which is optimal with respect to this rescaled cost, CT. And that corresponds to choosing a particular triangular factorization of the covariance matrices in these Gaussian source and targets. And we could compare that to the linear map that is exactly, actually, I apologize, these should actually be reversed with respect to each other. The map that's optimal on the bottom here with respect to the CT cost, and the map which is the conditional Brenier map, which is exactly given by a triangular factorization of the covariances. What we analyzed for now is just if we can consider a plug-in estimator for these maps that are optimal with respect to the rescaled cost, just by replacing the covariances and the means with their empirical counterparts, then we can show that if you choose this parameter in the that defines the rescaled cost t in a particular way with respect to the number of samples, then you can get estimation error, which decays as not quite the mean squared error going down as 1 over n, but just slightly slower than that. And we think that this probably can be improved. It's really just a function of our analysis.
So is this square in this a square a minus 2 there, or square root?
This, so it is a square because we put the a inside the norm. Yeah, so it's actually, so if I go back to here, it's inside the norm. Yeah, but yes.
Can you comment on where you think the slackness in the analysis comes from? Is it like the entropic approximation gap? I mean, the epsilon bit?
I actually think it's probably actually in both. So I'm not. I think there's a few things, but I really at the moment I can't say for sure which one.
I recall that Aram and John had some bound on the approximation quality of the EOT barocentric projection versus the Brenier map. I think that was loose back when they were just estimating, the vanilla map.
Yes. So we do rely on those results to balance the error from TT to T epsilon T, essentially. But then furthermore, we also have this error from choosing this rescaled cost. So I think it's really in both. Yeah.
So can you go to the slide where you show the rate result?
Yes.
So I'm a little bit confused. So TCB is the optimal transport map between two Gaussians, right?
Correct. Right. So these, in fact, should be reversed with respect to each other. There's a small typo in the slide.
Okay. But then it's really then a parametric problem, right? You're just estimating the mean and the covariance. Is that correct or no?
Yeah. So here we're just analyzing this plug-in estimator that just takes the mean and the covariance, rescales them to define this plug-in estimator for the map. And then we study the plugin, the map based on this plugin estimator.
So does this estimator have anything to do with the entropic regularization that you showed before?
No. So for the estimation
this is
rates, we're not
different, right?
accounting for the entropic.
So then why shouldn't this be the parametric rate? That is what is confusing me, right? Because this is like two parametric distributions. You're just transporting between them. Is that correct? Or?
Yes. That's a good point. So I really think this is probably just in the looseness of the analysis is why we're not getting that. Although numerically we also see something that is approximately this rate. I'll mention. I'll show that in a second. So I just want to in the last few minutes just show a few numerical results. So the first is really on this point. So we just wanted to verify exactly how it looks like when we do transport Gaussian source to target, where we know the closed form map. We can estimate the error of the estimator with respect to the true conditional Brenier map. And we here compare two different estimators, this one based on entropic regularization and the a neural network-based estimator. And here we use our results to tune both the regularization parameter epsilon on the order of t squared, so this should say epsilon, and the parameter that defines the cost with respect to the number of samples. And we're roughly observing actually the same rate. So this is now no longer with the plugin estimator. This is the actual maps that are being estimated. This being said, we still think there's definitely a gap between the analysis and what we're doing here in practice. Next, we just looked at how these estimators perform for problems where we don't have the closed form map. So we considered, again, my favorite banana distribution, trying to sample from different conditionals of this distribution for these one-dimensional conditionals, these slices for x given y. On the right, we plot these generated samples using these maps for three different estimators: the EOT estimator, a neural network-based estimator, a nearest neighbor estimator, and a neural network-based estimator for two different values of the conditioning variable, where you can see fairly good agreement and capturing of both this unimodal and this bimodal distribution. And lastly, we applied this to a problem, an inverse problem of trying to recover parameters in an ODE model given observations of noisy observations of the state of the ODE over time. So in this case, the parameters, there were four-dimensional parameters that define the ODE dynamics. This is a problem coming from population dynamics. And the observations were, there were 18 of them over time, so of two different species in this model at 9 different times. And we compared, for this particular application, how the conditional distributions of the entropic estimator looked like relative to samples that you would get from what one can consider to be the gold standard for these types of inverse problems, using an MCMC sampler that does require having to know the form of the prior and the likelihood and the posterior density. And this is just a qualitative comparison, but you can see the kind of close agreement between these two estimators in terms of the correlations that they can capture in this four-dimensional posterior. So with that, I just want to conclude and take some time for questions. So here what we looked at is how to consider a particular form for transport maps that have this block triangular structure that can be learned from joint samples of parameters and observations. One can think of it also as images and text or any paired samples that we can collect in various applications and use them to sample arbitrary conditionals of this joint distribution. So conditionals, including those that we haven't, for observation variables that we haven't seen in our empirical data sets. We proposed an estimator based on entropic OT for this block triangular map that exploits the fact that you can find this map as a limit of OT problems with a weighted quadratic cost. And we provide some analysis in the Gaussian to Gaussian setting, the Gaussian transport setting. Of course, the future work is to extend a lot of this analysis beyond Gaussians into other, for other source and target distributions, and to consider other types of estimators. So, for instance, those based on flow matching or dynamic types of transport, as well as a problem which I'm quite interested in for these inverse problem applications of exploiting the fact that in many applications, the source and the target might, even though they might be very high dimensional distributions, they might only vary with respect to each other in some low dimensional subspaces. And how do we automatically build estimators that can adapt to that structure? I'll just kindly point you to our reference on arXiv, as well as code to implement this estimator. And thank you all very much for your attention.